We've all heard about Newton's laws, and you think those laws are just laws. We observe things and that becomes the law. Well, I'm here to show you that there's a single principle where we can derive the same things that Newton came up with. If we use this principle of least action, then we can find out that really Newton's laws are really just extensions or derivations of this principle of least action. And we can describe all of motion of any dynamic system that's moving in terms of this principle of least action. Now, it should come as no surprise to you that this principle of least action, in order to derive the laws, we need to use math. And the math gets ugly. So, if you want to skim through the math and some of my drawing boards, I won't be offended because it's tough. But maybe my verbal explanations along the way of these mathematical uh, processes to derive Newton's laws will help because I share your frustration with complicated math. Like in other videos, I will go to the drawing board and start sketching out, or at least have pre-sketched versions of what I want to talk about. So get ready for that following. I'm going to start with two types of energies, and these should be familiar to you, but let's kind of start from scratch and say that we don't make any assumptions here. Kinetic energy, just by its name, kinetic, indicates that this is things that are moving. So it has to depend upon velocity. Now, velocity is a vector, so it can be either plus or minus, but that does not make any difference to kinetic energy. For that reason, we're going to say that kinetic energy is proportional to v squared. So there's velocity squared. M is there because it's proportional to the mass. Now you might have thought I was going to put 1/2 mv squared, but until we can justify a 1/2, this is all I think that we should put up there. Potential energy. This is something that does not depend on velocity. This is velocity part of energy, and this is potential energy. If we have no movement, then pretty much all we have is potential energy. Potential energy is a function of not time, but of position. And position, or this is the position really, we can talk about that as the environment that this dynamic system is operating in. And that position is going to change, the actual position is going to change with time, but we really need to know what the potential energy is going to be at any position. So I'm going to think of the velocity, the velocity, the potential energy represented by the capital V as a function of position. S. This is what we're talking about in this principle of least action. The S represents the action. So in order to define what this action means, we have to come up with some mathematical symbols that will make this more real. The action is the integral, which is the sum of all these different things over the interval of time. This is a definite integral. In other words, the limits are t sub 0, that's the beginning time, and t sub 1, that's the ending time of whatever this path of action is that we're talking about. Inside this parentheses, I've got kinetic energy minus potential energy. So if we have no kinetic energy, we're standing still, then we have a negative potential energy. If we don't have any potential energy and it's all kinetic, which I guess that's possible too, then the V, or the potential energy variable symbol capital V, goes away. Now, let's try and absorb that. The difference between these, and how does this action really going to play into bake? I've printed this out. The principle of least action states that among all possible paths x sub t, in other words, those are the different x's that the object follows that connect the fixed endpoints, the starting point and the ending point, is the actual path taken is the one that makes the action S minimal. Let me do a little bit of drawing here for that. So we want to circle that minimal. So least action or minimal path is maybe a best way to talk about that. Now, how do we apply this? I promised that we were going to use these ideas to derive Newton's laws. So we still have some more work to do. Do you realize that what this video says is that Lagrange actually came up with a law that simplified Newton's 3 laws of motion? And this law doesn't counteract Newton's laws. They're still true, but if you want to approach very generalized problems like exist in quantum mechanics, then you need this principle of least action. So this video is really important if you want to go on and work with the quantum mechanic videos that I'm coming up with. Capital letter L represents the Lagrangian. He's Italian, so that's how you say that name, Lagrangian. He came up with this set of new mechanical ideas about 100 years after Newton proposed his 3 laws of motion. The Lagrangian, as we saw from that last screen, equals the kinetic energy, T, which stands for action, and V, which stands for potential energy. This is kinetic energy, this is potential energy. So let's talk about the kinetic energy as m times v squared. Now you might be expecting me to put 1/2 v squared, but don't worry, we'll fix that later. The potential energy of one of the most common things that we deal with is the force of gravity. And potential energy is represented by mgh. X, not h, x, which shows the distance away from the center of the earth. So as you go farther away from the center of the earth, the potential energy gets greater. You drop the object and it goes and hits the surface of the earth, and then you have 0 or maximum kinetic energy before it gets slammed into the earth. Now, how are we going to find the least path? What's the least path? Well, here's how we're going to do it. First, I'm going to take the derivative of L and just look at the time elements that are existing. So that means we're going to really focus on the kinetic energy and what changes occur over time and not worry about potential energy because it's not governed by velocity. So if I take the partial derivative, in other words, just the partial change and just focus on the t's, this is what happens. Partial derivative of mv squared with respect to time minus change in potential energy with respect to time. Now, this might be a little bit of confusion because you say, well, the potential energy is going to change with time. Yes, potential energy does change with time, but it's a function of x. It's a function of position. So as far as position is concerned, there's no change at all. So if we take the derivative, take the 2 using the exponent rule, take the 2 out front, that's going to give us 2 times m times the derivative of velocity with respect to time. Okay? And the change in velocity with respect to time happens to be acceleration. Let's look at the partial derivative of L. Now let's just concentrate on X, the position thing that the potential energy thing comes up with. Well, that's going to be the change of kinetic energy with respect to position. Yes, the kinetic energy changes, but the kinetic energy is a function of time, how fast time is changing and how great the velocity gets. So that one's going to go to 0. And the derivative of mgx with respect to x, the m and the g are constants, so that just comes out to be mg. Now let's put all this stuff together. The minimum of L is going to be the minimum of the kinetic energy minus the minimum of the potential energy. And then we get 2 times ma equals mg. Well, this doesn't work out quite right because it said this is actually the force above the Earth, gravitational field times the mass. You got more mass, you got more gravitational force, and that should just be F equals ma. So let's see what we can do to fix that. I'll go to the brushes. We know that F equals ma, so this is really, let me reduce the thickness here. That just looks ugly. So we know that what we would want to see is F equals ma, or F on one side equals ma. We know this to be true. You can measure this and prove that that's the case. So really what we needed to do is divide by 2, divide by 2, divide by 2, and divide by 2. So we can change our kinetic energy to what you would expect it to be, 1/2 mv squared. Now, this isn't magic. This isn't a fudge factor. This takes what is known and observed and plugs it in for the kinetic energy. Now that has shown that the Lagrangian principle of least action, we can prove Newton's second law. Now we can also prove the third law, and we won't do that in this video.